Hello, this is Mr. Weiss, and this is the 10C live stream for June 11th. And we'll continue talking about the Tacoma Narrows Bridge a little bit today, and then we're going to work into some review material or new material, if you don't remember it, about forces to prepare you for 11th grade. So away we go. And I've got a couple people joining me, so let me know when you're there. Say hello so I know who I've got. And that will be great. I hope we get as big a turnout as last time because it was really nice. How many did we get last time? We had like 20 of you. So greetings, and yeah, say hello so I know who I've got. I see a couple people already out there. And there's kind of our goal for the start of the hour. We began it last time when we had a live stream failure from my part, unfortunately. Nothing I could do, but I could not get back online to finish it. So Tacoma Narrows Bridge collapse. Hopefully you've seen the video, and we're going to talk about two explanations today. So welcome to all of you. There are some folks, so welcome Christian and Isabel. And we'll give folks a couple more minutes to join us, and then we will begin. I think I see you guys in class next week. I hope so. If I do, we're going to try and do a couple of demos, if I can figure out how to do them in an English room or wherever I'm at with you. And then we'll continue with some stuff on forces. Good, Kira's here. Welcome, Kira. And Pia is here. She'll watch it later. Thank you very much, Isabel. That's just okay. Stuff happens. Good. Hopefully some others will join us. Got 4 of you so far. That's a good beginning. Last time we had really good participation as well. Not only on the physics, but on giving me feedback for how things were going in Corona world and online learning. Ooh, now I have 3 of you. I hope I actually have 4. Hope someone didn't leave me. Okay, well, you know what? I'm going to go ahead and start. So here we go. Let's just review a little bit, and maybe folks can say hi as they add on to our live stream. So last time, and in the video that a lot of you watched, was the Tacoma Narrows, and I had a diagram much like this. It's a suspension bridge, so there's 2 towers, one on each side, and in the middle, it's not up that much, but it is a little bit raised. And what you have is, that I didn't draw, are the suspension cables that help to hold the bridge, like that. Similar bridges are the Golden Gate Bridge and the Brooklyn Bridge, if you've been to New York City or San Francisco. Lucas is here. Welcome, Lucas. As is Felix. So, Tacoma Narrows Bridge collapse back in 1941. There were 2 things that happened. Back in 1941, the Tacoma Narrows Bridge collapsed. If you saw the video, if you haven't, go watch the video. It's like 3-4 minutes. It's pretty amazing. So, what's one theory? This is about where our live stream got cut off last time. From you, what's one theory or one way from the physics you know that you think the Tacoma Narrows Bridge might have collapsed? So let's get a little help from you. One of the ways all of you should know. I'm getting my markers ready for your explanation. Why did the Tacoma Narrows Bridge collapse? Give me one answer. Give you a minute to type. And I know sometimes when you send something off, it takes a little while to reach me. But I'll give it another minute. I hope you have some ideas. Usually you do. And another person or two has joined me, so let me know if you're here. And I hope you're typing, what's your explanation? What destroyed the Tacoma Narrows Bridge? I'm guessing you're giving me more than a one-word explanation, which is good because it's taking you a little time. And I'll give you one more minute. I'll give my computer one more minute to come up with something, and then I'll continue on if you don't. I hope my live stream's working okay today. Send off your explanation. In a couple of weeks, I'll get it. No, I hope it's less than that. Also, I look forward to seeing you guys. I think it's next week when I actually get to teach you. I'll try and make it worth your time. No explanations? Or is my screen frozen? Ah, now they're coming in. Okay, all at once. Thank you. Pia mentions the natural frequencies matched up. Good. Felix, there was an earthquake which had the same frequency as the, I think not bride, but bridge. I mean, thank you, Felix. Good. Let's look at those two explanations. Yeah, it has to do with, one explanation has to do with natural frequency. And what's the magic word these two are really talking about here? It wasn't an earthquake, Felix, but what maybe matched the natural frequency of the bridge? And that caused the bridge to, So what's the word that we need to know to say what destroyed the bridge? When the natural frequency was matched, it caused the bridge to do what? What's the word? Yes, I know it's been a couple weeks. Ute. Oh, now we're getting a bunch of stuff. Natural frequency, matching natural frequencies, right, Kier? Christian, forced resonance. Not forced resonance. You just mean resonance. Yeah, good. Right, resonate. Good. Okay, and it is, Christian, you're right. It's the wind that provided it. Now, in the videos I've seen, they talk about the wind speed having no effect on the bridge, but the wind direction did, and that's what the engineers didn't plan on. So one day the wind came from a somewhat different angle and caused the thing to resonate wildly, to oscillate wildly, to resonate. Okay, so one explanation is that the wind matched, and you can see why I'm talking about this. It reviews the physics we've had, doesn't it? The wind matched the natural frequency, and I'm going to abbreviate that because you've had it so often, of the bridge. Whoops, period. Ooh, don't fall over. Again. So wind matched natural frequency of bridge. Bridge resonated. There's our keyword. And as resonance means, and there's Luca. Thanks for joining us, Luca. As resonance means, it means there's a big amplitude. So if you saw the video, it's doing this, isn't it? First off. Okay, so the wind matched the natural frequency of the bridge. Bridge resonated, and too much energy was essentially absorbed by the bridge, wasn't it? Until it collapsed. Helen's here today. Welcome, Helen. So too much energy absorbed by bridge. And we saw that through a high amplitude, right? Remember the height, the amplitude, half the height is the amplitude. I'll see a high amplitude oscillation. I know I'm writing more than I thought I would here. Okay, let's begin again because a couple of you just joined us. Oh, I got some others joining us too. Hey, Amelie made it. Good. There she is. Leah made it. Dynamite. Now my crew's coming in. I'm happy. Good. I think I'm caught up. Okay, let's go back. I'm going to tip this a little so you can see it as well, all right? Hopefully I won't destroy my whiteboard again. So it says the wind matched the natural frequency of the bridge. The bridge resonated and too much energy was absorbed by the bridge. So we had a high amplitude oscillation. And that high amplitude oscillation eventually destroyed the bridge. Okay? That's one explanation. The other one, oh, Henry's here too. Thanks, Henry, for joining us. Good. The other explanation has to do with another physics idea we had. Okay? So I'll make here a spot for two. Okay. For two, I'm going to run out of room, so I'll use part of this and then I'll use the next board. You all right there? You can see some of that. Ooh, stay. Okay. Okay, so this time we're going to go and like I did with the guitar last time, right? Remember the guitar? And I made the string go up and down in the guitar. Let's work with the guitar first. So here's the guitar. Okay. So I pluck the string and the string goes up and down. And we said the string hits the end and comes back and hits itself. So essentially, the wave interferes with itself when I have a string going up and down on a guitar. Okay, like this. What's that called? It's called a wave. Did we have that? When a wave interferes with itself, can somebody type in, what is that term? Just so I know we've had it. A wave interferes with itself. What's that called? And on a guitar string, that happens every time you pluck a string. See if we've had that term. My live stream's a little slow today. Not you, just the responses I'm getting are a little slow. So wave interferes with itself, what that's called. We did it with a coil in class. I did it with a student, and we had a coil go up and down between us. Remember that? We said the wave was interfering with itself because it kept bouncing back from the ends and then hit itself as I continued to send the wave in one direction. What was that called? It's an important term, and I need it for our second explanation. Okay. Wave. Starts with an S. S, wave. What was that called? I don't know if it's just the internet slow or I'm just not getting responses from you. I'm guessing the internet because normally you respond pretty well. What is that term? A wave interfering with itself. If we haven't had it, can you let me know? But I'm 90% sure we did have it back in the pre-corona time. Wow, nobody's responding. Wonder if it's my browser. I'm gonna go a little low and see. No, that's the end of what I'm getting. All right, I'm gonna have to go on and just tell you, okay? Especially for folks that are gonna watch it later. So another theory as to what destroyed the Tacoma Narrows Bridge is, I guess I'll keep the same color, is a standing wave. So a standing wave, and there's really two parts to a standing wave. So here we go. Here's like the guitar string, but it could be the towers on the bridge as well. Remember the wave goes up and then oscillates down? I know the bridge doesn't do that, but my guitar string did. And the spot that has the most energy, where it goes from the highest high to the lowest low in the middle, is called an antinode. That's where the crest meets crest and trough meets trough. And these guys, where the tower is on the bridge and where the ends of the guitar string are here, these are called nodes. So one standing wave we had when the Tacoma Narrows bridge went like this, okay? And so I had an antinode in the center, and I had nodes. Think no movement, where my two arms are, the elbows, and those would represent where the towers are, okay? We had another movement, which was really interesting as well. Do you remember, those who saw the video, that at one point it didn't just go up and down, but it also started to do this? Now, isn't that bizarre? So a secondary standing wave came into being when the wind hit a whatever direction and frequency, okay? I hope you're still there. I'm not getting any comments at all. Maybe it's just my computer. Hope you're still seeing me. Sorry, I can't see your responses. Very strange. Probably all come in all at one moment. So with this other wave, I'm going to kind of ask you what that is, but I'm probably not going to see your response. Where are the nodes and antinodes in that part of the wave? Remember, this was the road bed, and in addition to this, it started to do this. Where is there a node? Well, if you said right in the middle, you're right. So there's my middle finger, and that's where the node is. And the antinodes are on the edges of the roadway where those light poles were, if you saw the video. Isn't that wild? So a second type of standing waveform, not just the first one, but a second one as well. But frankly, the first one, I think, looking at the video, is what destroyed the bridge. So a standing wave, and now I've got to change, hope you have all that. I've got to change whiteboards. But I'm going to put that one down, put this one up here. Okay. A standing wave, recall, has the energy is concentrated in the antinodes. In the antinodes. And then there's essentially no energy being transferred in the nodes. And nodes are probably where a crest is hitting a trough, so to speak, if we think of it as a transverse wave. So nodes, think of no energy transferred. So another way of looking at the Tacoma Narrows Bridge is, hey, folks, with this thing creating a standing wave and the energy being transferred here and being absorbed and accommodated by the center of the standing wave, the antinode, too much energy was just there and the bridge collapsed, okay? So there was too much energy in the antinode portion of the bridge and the bridge collapsed. I'm going to write that, then I'll tip the board so you can see it. So bridge collapsed when, wow, my screen is still frozen. I can't see any of your responses. I'm sorry about that. I like it when you respond. I wish I could see them. Okay, bridge collapsed when antinode part of the standing wave held too much energy. Too much energy. Some things can hold out and have that much energy, but some things can't. And for that poor bridge, the standing wave, the antennode had too much energy and the thing collapsed. Now, again, I think physicists would look and say both explanations are reasonable explanations. Both have to do with the physics that we've learned this last semester, okay? Cool. Hope you can read that. I'd ask you for questions, but I can't read anything you're sending me right now, and I don't know why that is on the live chat. I don't think I turned anything off. And I'm as low as I can go here. I'm going to type something. I'm going to type, "Are you all still there?" And see if I can see that. Well, I can see my little message. I hope you're still there, especially after our fiasco last time. Oh, now I'm getting tons of responses. Holy moly. Okay. I don't think so. Could you send the notes to the classroom? Oh, no, you can't see me? Okay. So some are saying yes, they can see me. Some not. Okay, Helen says we can see you. All right, that's good. That's good. All right, then I'll continue. All right, thank you. Okay, one last fun thing that I'm going to write here is because a lot of you are in the band and so on. Here's another. Here's a drum. You like my drum? Beat the drum. Bam, 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 bam. Where's the node? Where's the antennode for a drum? Can you guess the parts? We could sue you, but I wasn't done writing down the notes. Oh, okay. All right. I'm going to hold this up again for a moment, and let's see if I can help out with Leah writing down the notes. I'll try and tip it so she can see it. I'll give you a moment here. Yeah, we're still doing okay on time. Give you a moment here, Leah, and maybe others. Okay. Okay. Remember that stuff now on nodes and antinodes and standing waves? I hope so. Okay, so last thing is, for my drum, where's the node and where's the antinode? Good, Leah got it. Okay. Well, if I pat a drum, the antinode will be where most of the energy is, and that'll be in what part of the drum? And the node will be where the energy is not. Good, I got some responses. Antinode in the middle and nodes around the outside. Dynamite, node on the outside. Hey, Pia and Christian both got it. Good, so I'm going to put an A here for the antinode. That's the middle membrane of the drum. And around the outside, believe it or not, it's a circle in blue. That's where it's not moving, and that's the node. How cool is that? So the antinode's in the middle, well done. And so A stands for antinode. And the node is the outside ring. Isn't that kind of cool? In my guitar, it was the ends that were the nodes, right? And the middle was the antinode, but I think you know that already. Okay, you got it right, Kira. Nodes where particles are at rest, and antinodes, particles move fast, or at least they have a lot of energy at the antinodes. Right. And yeah, good. And Felix had it too. Okay, good. Thanks for your participation. I'm happy that you're there now. Okay, let me tell you what's up. You've pretty much covered the curriculum that we need for grade 10. And what I've done in past years is I've asked my physics colleagues, Herr Wiechert, Frau Gorges, Mr. Blessman, Frau Ruckgeis, what students need for ABI or diploma program physics in 11th and 12th grade. And they all said the same thing. So we're going to spend today, and when I see you live, I think it's next week, reviewing something you had years ago, okay? So I'm going to erase. I think I'm going to keep the big board. This is a lot simpler. I think I'm going to erase this one if it doesn't fall over and use this right here. So let's make sure everybody's got that. I'll tip it so you can see anything that was blocked by the glare. And I hope you have that now. And let's use that to talk about something you need, which you haven't had in a couple years. And that's this idea called force. So we're going to review and apply the idea of force. Okay, so your turn to type now. What is force in physics? A force is a what? What is a force? See if you remember from a year or two ago. I don't think I reviewed this with you this year, but I don't really remember. A force is a or a And I'll wait a minute to get your responses, and then I'll assume I'm locked up again if I don't get it within a minute. But thank you for responding, those who did. So what is a force? All right, well, I don't see responses. Oh, I'm seeing some. Energy, it's not really energy. Causes a change in object's motion. Yes, good, Isabel. That's a nice physicsy way to describe it. I'm going to say, first of all, it's a, anybody the one? Okay, it's a push or a pull. So P or P, push or pull. But I like what Isabel said. It does cause a change in an object's motion. So, which causes a change in an object's, well, I can't spell today, sorry. In an object's motion. Good. Okay, so there it is. So force is a push or pull, which causes a change in an object's motion. Let's see what other people wrote. Yeah, good. Christiana had it as well. It has to do with action. Yes. Kellen is here. Oh, hello, Kellen. Welcome. Good. Good. Okay, so what I want to ask you now. Let's do some, ready? Here we go. I'm gonna do, so I'm gonna do a force, ready? And so I change the motion of this little eraser, and I'm gonna pull it, and so both of those are little tiny forces, okay? Okay. Lucas Moscow is here as well. Okay, so what is force measured in? What sort of label or Einheit or unit? Okay, what do we measure those in? So measured in rank. Oh, some of you got it right away. Oh, I love it. Yep, Pia, Henry, Christian, Lucas, they all know it's measured in newtons. We're not talking fig newtons, right? We're talking about newtons after the famous guy, right, from the 1600s, Isaac Newton, professor at Oxford. We're going to look at his ideas in a second. And Leah has it as well. Good. So a newton, ready for this? 1 newton is a kilogram basically under the influence of gravity, if you like, times, remember the label for gravity? The gravitational acceleration, I should say. So gravitational acceleration was meters per second squared. So a newton is this wacky label but it makes sense if you think about it. Oh, it's a kilogram influenced by the acceleration of gravity, which is meters per second squared. So it's kilogram times meters divided by second squared, okay? A Newton is not very much. I'll try and bring a Newton scale or two so you can remind yourself if you had those in 8th grade. So if I pull just like a little bit, I'm going to get in a Newton or several Newtons, okay? Force can be measured in other things as well, like pascals, or in chemistry, we use the term atmosphere for the pressure, the push of the air down on us. But in physics, the most common one is in newtons. Great. Okay. I don't remember when Isaac Newton lived. You can Google it. But I do know that he came up with 3 big ideas about force. And let's review those, okay? So we got, we call them Newton's laws of force. I'm going to say Newton's 3 laws of force. There. And while you're catching up, I'm going to race the other board. So say goodbye to Tacoma Narrows Bridge. Oh, don't worry, it's been replaced. There's a better one there. Been around since 1940, whatever, when they rebuilt the thing. It better be good. There's a lot of wind out there. Okay. We good? I think we're good. Okay, so Newton's 3 laws of force. Let's review these suckers. And then we're going to do something more 10th grade-ish with this, all right? So don't worry, I'm not going to just review 8th. I'm going to try and challenge you too a bit. Okay, so the first law is called the law of and you'll fill it in a little bit. Maybe you know it already. But I'm going to start the law and somebody's going to finish it, okay? An object in motion does what? Okay? I want you to finish that. Good. Christian's got the word as well. Thank you, Christian. Called the law of inertia. And now somebody else can have it. Y'all had this in 8th grade or maybe even in the Grundschule, okay? An object in motion tends. Can someone type out some of the rest of the law for us, okay? So an object in motion tends to blah, 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 blah. Can you give me more of the law? The rest of the first law. An object in motion tends to what? And then there's more of the law after that. So if you could type. Christian's got it. Let's see if some others come up with it. Can piggyback on that idea. Yeah, and there's a little more to it, than just that. So let's see if we can add to Christian's idea. See if someone else can pull it out of their deep, murky brain for us. Anyone else got it back there in their brain and could help add to? Yeah, Felix Barco has it as well. Remain in the state of motion unless an external force acts on it. Nice, good. Okay, let's put all that together and begin. So an object in motion tends to stay in motion. And an object at rest does what? Let's see if some others have it as well. Good, Kira does. An object at rest tends to stay at rest. Good. So an object in motion tends to stay in motion, comma, and an object at rest tends to stay at rest, unless, and I'm going to take this from Felix now, unless acted upon or acted on by a force outside the system. The system's whatever I'm dealing with. So as Felix said, we call it an external force. Unless acted on by an external force. Well, let's read that back and take out the blur, huh? Okay, law of inertia. An object in motion tends to stay in motion, and an object at rest tends to stay in rest unless acted on by an external force. Good. I'm sitting here. There's not really much I can do to give you examples, but I want to try and figure out something. We'll see how creative I am, and you can give me some examples of this too. Yes, exactly. Good. Okay, so here's a really not so interesting example. Okay, if I shove this and give it a pretty good force, it'll keep going. Okay, unless I act on it by an external force, unless I act on another force and stop it. Okay. Now, of course, that ignores some other forces like friction, which of course is happening here. Let's take the pen cap off. Maybe my example will be a little bit better. Okay, so I'm going to give it a roll, and yes, it does indeed roll. And it rolls pretty good, but there's still some friction. That's my external force. If I was in outer space, I could really do this well, right? I could take it in outer space and throw it. There's no air out there. And if I throw it, the thing will continue with the same speed, right? Which Kira and Christian and others have said, the same speed or velocity and the same direction until some other force acts on it. And out in outer space, that could be a long, long, long time and a lot of distance before it hits anything at all. There's a lot of nothing in outer space, a whole lot of nothing. Okay, so let's do some examples. I'll say pen rolling keeps rolling. Let's see if you've got some examples. Okay, I've got this thing. You as the laptop are sitting on this Entfeuchter, this reverse humidifier thing. It weighs a ton. So if I push this, this is kind of like the second part of it, isn't it? The second part. An object at rest tends to stay at rest. Okay? So if I don't give it enough force, that sucker's going to stay at rest. Same with my chair. I got to give it a pretty good force to get it moving, right? Maybe you can think of some other things, big and small things that will keep going unless you put a force on it. I like to always talk about elephants, okay? You see this elephant in front of me? It's huge. He barely fits in the room. And he's one of those little tiny Indian elephants. He's not the African one. Watch when I try and push it. Man, that sucker really remains at rest, doesn't it? Remains at rest. It's a big elephant. So it doesn't really want to move much on its own. Let's look at that word that Christian knew, inertia. It's part of the first law. And it goes like this. Inertia is the resistance to changes in motion. All right, if it's got a lot, well, if it resists changes in motion, it's got to have a lot of inertia, okay? Think of you, right? You're laying in bed in the morning. You don't want to get out, right? Somebody try and push you out. You got a lot of inertia. They're going to have to push you pretty hard, aren't they? Okay, so that's the law of inertia. You're an object at rest, staying at rest if you're stuck in bed, okay? Resistance to changes in motion. More mass, like my elephant, not surprisingly, gives you more inertia, doesn't it? Have you had that word inertia before? I guess Christian has. Have others of you, does that ring a bell from 8th grade or from some other course, inertia? Sometimes we use it even in English class, like for Mr. Felt or somebody, whoever you've got, where if something has a lot of inertia and it's already moving, we could say that idea has a lot of inertia. It's already moving, and no, you have not, and you have not had that word. Oh, then it's a new word. We really do need to talk about it. It's an important word. So sometimes an idea can get a lot of inertia. Like right now in America, there may be some ideas to change laws, and there may be a lot of inertia changing some laws about police or whatever it is. So we could use that physics word sometimes in an English way as well to describe something. We could also say that certain things have a lot of inertia, and so it's difficult to change. In that case, we're talking about the at rest part. You know what I mean? I'm not saying we use this all the time, but it can be used in an English sort of way as well as a physics way. But the first law is often called law of inertia because it has to do with things that tend to either keep going or have a hard time getting them to move to begin with. Okay? I think you're responding now, and I can see your responses, which makes me happy. Any questions from you about inertia? The Earth certainly has a lot of inertia, right? We keep on this beautiful spiral path. Now, I know we have some forces due to gravity and other things, but in general, we also have a lot of force going forward around the solar system as we move forward each day, right? Same with our moon going around us, right? The moon has a lot of inertia. You wouldn't want to be in the way of the moon. You'd be hit by a big object as well. Good. Anything else I want to tell you about inertia? Generally, we're going to ignore the force of friction when we're discussing this, okay? Why? Because as soon as I start to move something, let's say I move the folder on my hand here, as soon as I start to move it, I get friction. And it works with the physics, but it's hard. It makes things more difficult to understand, okay? It does follow the first law, but you have to then think about friction as a force as well. But we're going to ignore it for our thoughts. Right now, I'll just say the folder stays where it is because it's got enough inertia, so it's going to not just start floating around the room on its own, okay? That's kind of what the first law was about. Huge. Good. My people, I'm going to see you, I think, next week. We're going to continue with forces, and I'll take any other questions you got on bats or earthquakes or anything when I see you live. I might have a demo or two if I can figure out how to do it in the English rooms where I'll see you. Until then, I think I'm going to cut off a minute early because it's a good place to stop. We'll continue with the second and third laws and some more 10th grade ideas on physics when I see you. So be well, and I look forward to our live meeting very soon.